If you want to estimate what the uncertainty will be when you go to make some measurements later on, you can start off by measuring the error that you get under controlled conditions. Now, for those controlled conditions, you need to know what the applied temperature is if you're working with temperature, or the applied pressure if you're working with pressure. All of the things I'm doing here with temperatures apply to any measurement you want to make. So if I could carefully control my environment to give it different temperatures between 0 and 80 degrees Celsius, then I could put my thermometer into that environment and make measurements with it to get a measured temperature. Now, in a perfect world, when I had 0 in my environment, I'd measure 0 on my thermometer. When I had 40, I'd measure 40. When I had 60, I'd measure 60, and so on. But we know we don't live in a perfect world. We know we've got some uncertainty. And what we should actually see is a collection of data points that looks something like this, very close to, but not right on that straight line. So this variation around that straight line, that's the size of your uncertainty. And if it doesn't look like a really obvious straight line between the applied temperature and the measurement temperature, then you really need to rethink your instrument and think of a better way to make measurements from an engineering standpoint. So this graph of applied temperature versus measured temperature is really reassuring to tell us that all of these lie on a straight line, but it's really hard to tell about how big is the magnitude of those errors in actuality, because wherever we've applied, say, a temperature of 40 degrees and we've got a temperature of 41 degrees, that implies an error in our measurement. It's not an uncertainty anymore because we know what it should read. It should read 40 and it read 41. So we've got an error of 1 degree. We can get a better idea by plotting just those errors, the differences between the straight line and those data points, as we go over a range of temperatures. So in this case, I might wind up with some data points that look like this. And let's fill in a whole lot of them around here. And there's lots of them that are actually fairly close in there. So I've got some scatter in my data. And if I was to eyeball this, I would say that, yeah, probably in a range about like that, about plus or minus 1, I've got 95% of the values. So just looking at a graph like this, it'll let me say, yeah, eyeball, this is about plus or minus 1 degree Celsius. And very often that's accurate enough. It tells you roughly how good your measurements are. Now, if you want to get a little bit more involved, you can take this data and do some statistical analysis on it. For example, if I calculate the standard deviation and the mean, I can find out, well, it looks like this data is a little biased up in this direction. So the mean will tell me if I've got any bias error, i.e., if the mean sits up here, then that tells me I could get rid of that bias error by calibrating, by just changing all of my readings down if I had an adjustment screw on the thermometer or if I did it in my post-processing. Standard deviation tells me something about the spread in the data. How much does it spread around the mean? And the bigger the standard deviation, the larger my uncertainty. And in fact, if I have a Gaussian distribution, and we're going to assume that usually, then I will say that the standard deviation times 2 gives me my uncertainty. With a 95% confidence. So the simplest way to get a pretty good uncertainty estimate measure a whole lot of errors, make sure that the mean is small, or if it isn't small, that you adjust your measurement technique to make it 0, and then calculate the standard deviation. And 2 times the standard deviation gives me my uncertainty at 95%. If I have a Gaussian distribution, I've got a curve that's got a shape something like that. There's the mean, and there's 1 standard deviation, holds about 68%. There's 2 standard deviations. So 2 times the standard deviation, whoops, not all the way across, that would be 4 times. 2 times the standard deviation out from the mean, gives me my uncertainty. So there's another way you can estimate the uncertainty. You can either start by just looking at this error distribution and saying, yeah, that's about plus or minus 1 degree Celsius, and that's usually good enough. Or you can calculate the standard deviation, and if you've got all that data, it's really easy in any spreadsheet or in Jupyter Notebooks or in MATLAB. Calculate the standard deviation, multiply by 2, and use that as your uncertainty value. So again, make sure that every measurement, say it's 24.7, includes a tolerance of, say, from this one, let's say we did our standard deviation calculation and we got 0.9 degrees Celsius. That information, both of those numbers, are really important to telling us not just what the temperature is, but how sure we are that the temperature is in that range. Again, these examples with temperature in degrees Celsius, it could apply to voltage, it could apply to pressure, it could apply to anything you measure. The approach will be the same.